Today's topic is fluid mechanics. Now, what are fluids? Fluids, unlike solid, are either gas or liquid. Primarily, these two categories are called fluids. Now, one of the principles in fluid mechanics is Archimedes' principle. What does this principle say? It says, if you have a trough of liquid and you immerse a body into it, either it may sink completely or it may float. Now, what happens when this body is dipped in this water? It displaces liquid which is equivalent to the portion it is dipped, right? And suppose you had attached a spring balance and initial weight was W1. You will notice if you dip it in water, in fluid, its weight as resisted by the spring balance will be less. Now this apparent loss in weight is equal to the weight of the liquid displaced. Now what happens if the weight of the liquid displaced is less than the weight of the body? Then the body will sink. And what if the weight of the liquid displaced is equal or more than the weight of the body? The body will float. So the condition for floating is weight of liquid displaced is greater than or equal to weight of the body. Right? So obviously, if this body has more density, it will tend to displace less liquid for the same volume. Okay. Now, second principle is Paisleys equation. What this equation says is, suppose you have a pipe in which liquid is passing from point A to point B in this direction. Then the total energy per unit volume of A of the fluid at A is same as total energy per volume of the fluid at B. Now, what are the energy components a liquid can have while flowing? First thing is the pressure energy. If pressure at point A is bigger than pressure at point B, it is capable of doing more work, right? Second thing is the potential energy. If a point B is at a higher elevation compared to A, let us say this is H, then obviously fluid at point B will have more potential energy compared to fluid at point A. Okay. And the third is kinetic energy. If fluid at point A is flowing with more velocity compared to fluid at B, then obviously kinetic energy of the fluid per unit volume at A is more than that of B. Okay, now let's put it down in an equation. The equation is pressure energy at point 1 plus potential energy. This was our pressure energy. This is our potential energy plus this is our kinetic energy. Now it is not written like half mv square because we are taking per unit volume. So when you convert it to per unit volume, the equations become like this. This is ρ1, h1, ρ1, v1. This is equal to all these parameters at any point, at any other point, which is right. Now, if you see, let us say pressure at 2 points are same, A, and their elevations are also same. H1 is equal to H2, and there is no change in density. Then what happens is, or sorry, our P1 minus P2 becomes what? If these two terms are same, then it is purely on account of velocity. Which means if you have a higher velocity at some place, then its pressure will be less. It goes inversely. If velocity is more, its pressure will be less. Okay. Now, a simple instrument to measure flow is called a venturimeter. It looks like this. You have point A, whose cross section is so much. Then it its cross section narrows down at point B. And again, then it expands to similar cross-section or maybe different. Then if we attach a manometer between these 2 points, what will happen? Because cross-section here is much lesser than cross-section here, the velocity at B is much higher than velocity at A, which implies that pressure at B will be much less than pressure at A. So you will have something like this. This represents pressure at this point. This level will represent pressure at this point. So if we know, if we can measure the delta P, then we can find out corresponding velocities. We can find corresponding velocity, we can find the flow rates. So this is a very simple technique to find the flow rate of fluids. Now next topic is surface tension. What is surface tension? Let us say you take a tumbler and you stretch some membrane on top of it. Then what happens is this membrane will try to pull itself in such a way so as to shrink it. Surface tension is exactly like this. It is like a stretched skin, which always tries to shrink. Now this property gives rise to a phenomenon called surface tension. And we will see the result of this surface tension in the following topics. Another term is called surface energy. When you're stretching a membrane over this glass, this tumbler, you require certain energy. Certain energy is created to stretch a membrane over this glass. So when you have a tumbler which has a free surface, this free surface has some energy due to stretching of water membrane. And this is called surface energy. Right? Okay. Now let's take a small experiment. We take a thin metal loop like this, open-ended. We take another wire like this, attach a handle to it. Now what we do is we dip the entire setup in soap solution. Then what we will see, that soap film is formed here. Now if you pull, if you apply force so that this wire moves from here to, let us say, here, it moves a distance x. Then some work is done because you have force against pulling and you move it to a distance x. Okay? Let us say this length was L. Then the force that you applied is equal to 2 times SL, because this is surface tension. It is measured as force per unit length. Since the length is L, so it is multiplied by L. Surface tension per unit length into the length. Now, why this 2? 2 because there are two surfaces created, one in the front and one at the back. So there are two free surfaces, and that is why this force becomes twice as much. So the work done would be how much? Force into distance, which is equal to so by stretching this soap loop from position A to position B, we have done so much of work, and this is surface energy. This is on account of surface energy. Because we have created more surface. Now, next topic we will talk about is excess pressure inside a liquid drop. Or let's not call it a liquid drop, just inside a drop. This is our drop. And let us say this is an imaginary section on the spherical drop. Let's call A, B, C, D, and on some other side we have point E and here F. Now let us say the atmospheric pressure here is P1 and inside the drop it is P2. What happens is there are many forces acting on this drop. And what are they? First is F1, surface tension, which try to create force toward the center of the drop. Second force is due to atmospheric pressure outside. This atmospheric pressure is trying to push from all the sides. Okay. Third will be due to pressure inside the drop itself. You have a pressure P2 inside, what it will do, it will try to put the pressure in this direction, away from the center. Away from center. Right? Okay. Now let's put an equation to it. We know F1 and F2 are working in the same direction, and F3 in the opposite. Since they are in equilibrium, these two forces will be, this sum will be same as this one. And how much is F1? F1 was what? Surface force of surface tension. How much surface we have got? We have got sorry, it is not a surface. The surface tension is acting on this periphery, on this imaginary line. Right? And what is the parameter of this line? Parameter of this line is 2 pi r. And this surface, this is surface energy per unit length. So this is the total energy force due to surface tension. And what is F2? Ft is due to pressure outside. Let's say we have pressure P1 and the area on which it acts is the area of this complete drop. And what is the area of the complete drop? Pi r square. Right? This is equal to this force, pressure inside the drop. Again, if we say it is P2, it acts on how much area? Pi r square. Okay. So what is P2 minus P1? This term divided by pi r square. We get what it means is two things. P2 is greater than P1, which means pressure inside the drop is more than the pressure outside, one thing. And the difference of the two is given as twice the surface tension divided by the radius of the drop. Okay. Similarly, let's try to calculate excess pressure inside a soap bubble. The soap bubble is like this, and it will have certain thickness. I'm just magnifying it for the sake of understanding. This radius or this radius is same because this is too thin. So this is R, and we may take P is the pressure inside, P3 is the pressure outside, and P2 is the pressure inside the thickness of the soap bubble. Okay. Then we have already seen what is P1 minus P2. Between this pressure and this pressure, we've already seen is equal to 2s pi r. And what is P2 minus P3? This minus this. Again, if we take this outer one as a sphere, again this is 2s by r. So what is P1 minus P3? What it says is pressure inside a soap bubble, difference of pressure inside the soap bubble and the outside the soap bubble is 4 times surface tension divided by its radius. Now, all of us have seen sometime or the other, if you have a trough of liquid, you take a small capillary, and if there is a liquid inside the trough, then the liquid rises in this capillary. Yeah, this is called rise of fluid in capillary. Sorry. Now, if you see carefully, if I magnify this diagram here, there is this meniscus, and if we draw a tangent to this meniscus, we call this as theta. The meniscus creates a force in this direction, which we can resolve in sine theta and f cos theta. This, because of symmetry, will get cancelled with the counter point on the opposite side. So what you will get is a net force, this one. So if we take this force over the whole meniscus, what is the perimeter of the meniscus? 2 pi r. If this is r. So the force acting will be surface tension at force per unit length into total length. Total length is 2 pi r, and vertically upward will be its cos component. Now this is the force acting upwards, and what it will cause? It will cause liquid here to rise. And what will be the weight of the liquid? Weight of the liquid will be pi r square, density, and g into h. H is the height. Pi r square is the area. Height, this will give you volume. Volume into rho will give you mass, into g will be the force. So our h becomes 2s cos theta divided by r rho g. This is the rise of liquid in thin capillaries, where S is the surface tension. This theta is called the contact angle. this theta, which the tangent of the meniscus makes with the wall of the capillary. Now, liquid will rise with theta less than 90. Now, if what happens if theta becomes more than 90? Instead of liquid rising up, it will depress. So liquid will be depressed if theta is greater than 90. Okay. Now, let us say this was our tube, which was sufficiently long, and water rose only up to this height. What will happen if we cut our tube to a height less than s? Would you think that liquid will continuously keep flowing because it can rise up to height h, whereas our tube length is much smaller? No, it won't happen like this. What happens is this meniscus will be adjusted in such a way, meniscus meaning this theta will be adjusted in such a way that it doesn't let the liquid overflow. Now what happens in that case is this was the total force acting upwards, and r square h rho g was the weight of the liquid acting downwards. Now in this case, theta adjusted in such a way that even if this h is less than the height to which it can rise, this h will be the maximum h available to us, which means cos theta will no longer be same value. It will adjust itself so that it accommodates this height. Let us say we call it this prime height. H prime is less than h. This h is the height to which, if we have sufficient length of capillary, it can rise to. So if we have a capillary of insufficient length, which is less than the height to which liquid could rise, the liquid does not overflow. There is no overflow. The shape of the meniscus, it may change like this, or it may change like this, whatever. The shape of the meniscus will change, thereby changing this theta angle, and this theta angle adjusts itself in such a way that this equation holds true. Next topic we will study is viscosity. What is viscosity? If you take a river, this is the river bed, and if you see the profile of the velocity of water, you will see as you rise from the bottom, the velocity keeps increasing and it is maximum at the top. So why does it happen? It's because you can imagine the whole height of water in terms of layers. When water flows, one layer slides over the others. And it doesn't flow over the other without any resistance. There is a resistance for the upper layer to flow by the lower layer. And this is because of the term called viscosity. And what are the units of viscosity? M, L minus 1, T minus 1 are the units of viscosity. And normally it is expressed in poise or centipoise. 1 poise is equal to normal second per meter square. Units. Quite often, since poise is a bigger unit, we use centipoise as the unit. Now let's try to calculate the force on particular layer of fluid. Let's say we take an area of fluid of an area A. This is our velocity profile. It is maximum at the surface. Z is increasing this way. Then the force, and then let's say we try to move this area by applying some force. Then the force applied will be equal to this is the force required to pull an area of A. Area of A. This is the viscosity of the fluid. And this is the velocity gradient. Right? Now, let's see. Flow of fluids inside narrow tube. Let's say we take a tube of radius r, length L, and there's a delta P across this fluid. If fluid is flowing like this, then pressure here would be more than pressure at this end. Only then it will flow, otherwise fluid will not flow. So the rate of flow is governed by an equation called Paisleys equation. Which says V by T, rate of volumetric flow inside a narrow tube is given as this is the pressure difference between the two ends. R is the radius of the tube. This is the viscosity of the fluid. This is the length of narrow tube. Then the rate of flow is given by this equation. Next topic is Stokes' law. You must have seen if you're going in a cycle, if you're riding a cycle, you feel as if somebody is trying to push you back. And what is that? That while you are trying to move in one direction, there is something which is dragging you back. This drag force on a body is governed by Stokes' law. What it says is, let us say that a sphere is falling down in stream of air or any fluid. Then this fluid resists its motion in the downward direction, which is called drag. So this force of drag is defined as 6 pi's, where r is the radius of the sphere, for example, and v is the velocity with which it is falling. Now you see, if a body is free falling, its velocity will keep on increasing. Now if its velocity keeps on increasing, what happens to the drag force? This is drag force. Drag force will also increase. And how long it will increase? It will increase till it balances mass, weight of the body. So a situation will come when V will no longer change, it will become constant. Because if it changes more than this, drag force will become, upward force will become more than the downward force, which will never happen. So a situation where our velocity becomes constant is called terminal velocity. So we define V as terminal velocity. If we use this formula, is given by, okay, we'll let's do some analysis. You don't write the formula straight away. Okay. Now, what is the gravitational force acting on it? It will be volume of the sphere, its density. Okay. This is the weight of sphere. Okay. And when this sphere is falling, it will experience a buoyancy force, which is equal to the weight of the fluid displaced. And how much will it be? Again, it's volume. This is rho of solid to rho of fluid into G. This force is acting downwards. This is buoyancy force acting upwards. This will be balanced by drag force. Let's call it terminal velocity. So when we rearrange these terms, we get is rho of solid minus rho. This is our formula for terminal velocity, meaning thereby, if we let a body fall down freely, it doesn't keep increasing its velocity. A stage will come when this velocity becomes constant. And at that time, we call this velocity as terminal velocity. And it is given by this formula, which is 2 times for a sphere. This is the radius of the sphere, gravitational constant. This is viscosity. This is the density of solid. This is the density of fluid.